Let's make this big. Let's go. Here. Big.
Nice.
Can everyone see this okay?
Looks good to me. Maybe one more bump though for the
One more bump. All right. Maximum size. Very nice.
Perfect.
All right, cool. So where we left off, I think fitting, I think will be our last session. We were close to the end on our checklist here. So we created this ZIO 2.0 runtime based on this idea of this nano actor that accepts messages into its inbox, and using that to simplify a lot of the concurrency problems of the runtime. And we implement forking, we implemented typed errors. We generalized that to include this concept of a cause of failure that could be either a typed error or a defect of me spelling Coke on my keyboard, or could be interruption. So we could represent interruption as a value and could handle that. And then we implemented support for interruption, and we made some progress here. We basically implemented the ability to control interruption. So to say there are certain regions where we want to be interrupted or we don't want to be interrupted because maybe we're doing something important, where once we start doing it, we need to finish it. We didn't quite implement this concept of masks yet. So I'd say we did the regions, but not the masks. We'll come back to that today. And then we've got basically the building blocks for finalizers, but we haven't actually implemented finalizers yet. So I think our goal for today is going to be to implement these masks and this concept of finalizers. And I think that'll let us declare victory here. Does that sound good?
Let's do it. Meow,
Awesome.
my cat says.
Meow. All right. So where we left off is we implemented this uninterruptible operator. And what this did was we got these runtime flags, which right now is just has one runtime flag. So maybe we're being a little bit prematurely generalizing there, but it has one runtime flag of whether we're interruptible or not. And what we do here is we check whether we're interruptible. And if we're already uninterruptible, then we're done, right? We already are this thing, so we don't need to do anything here. But if we're not interruptible right now, or if we are interruptible right now, excuse me, I got my double negatives off, then we're going to make ourselves uninterruptible. And then we're going to do this workflow here. So that's this ZIO. So we're going to run this workflow. And then when it's done, whether it succeeds or fails, we're going to set ourselves to being interruptible again. And then we're just going to either refail with that failure if we failed, or we're just going to return that original value once we're done restoring our interruptibility status.
Quick question: is this pattern maybe abstractable? It seems like this kind of thing might be might have a name in ZIO proper, where we want to
this is basically called on exit. So yeah, you could just basically implement this like def on exit, and it just it gives you some effect that you get to do with the exit value, and then we do that thing, and then it just refails with the original thing. So if we want to, we can implement it ourselves right now. I think it's one of these where sometimes there are like lots of ZIO operators we could like re-implement. But yeah, let's do that for a second.
Ensuring is similar as well, right? Ensuring basically is maybe another higher level above on exit.
Yeah, actually, I think ensuring would do what we need to do here. Let me go back to this for a sec, just so we can look at the signature. Yeah, so ensuring basically does something where it doesn't depend on how the thing finishes. So yeah, ensuring is probably actually the most specific operator that you could use for this. And then on X is more powerful than that. And then full cause ZIO is more powerful than that. So there's a whole little hierarchy here. Okay. So yeah, that's one we can implement here. So let's do that. Let's see where I am alphabetically here. All right, I'll just do it right
Best
here. So this will be ensuring, and it'll take something. So we want to say this finalizer is not going to fail. So this is going to be a finalizer that can't fail and can produce any value, because we don't care what it is. We're just going to throw it in the garbage can when we're done. And it's going to return back a new ZIO that's going to fail or succeed the same way. And so we could just do self dot fold cause ZIO, and then we'll have the cause question mark a question mark, and then yeah, I think it's even has it for me, so I'll just do finalizer ZIO dot seed a.
I mean, I'm guessing maybe you left this blank to do something else, but let me just fill in this stuff, and I'm sure.
No, I just sometimes I have this little pattern of like I do my parameters and my question marks first, and then I come back and I fill them in. But let me okay, we got this compiling. So now let me go back to my uninterruptible, and now yeah, I can simplify all this to be ensuring.
I guess one question is maybe I'm actually not sure. I would assume that ensuring is uninterruptible, right? What you put into there, whatever effect, does that become uninterruptible in real ZIO, or would you have to make that uninterruptible explicitly?
So there are some subtleties of how interruption works or doesn't work in our toy runtime versus the real ZIO runtime. So here our fold cause ZIO is able to recover from interruption, right? Interruption is just one of these causes, and it's just another cause, and you can recover from it, versus in the real ZIO, there's kind of some further depth to that, where interruption can kind of be deferred but never actually recovered from if you're externally interrupted. Of like, you know, if the guy's got the knife in your back, you can struggle on a little bit farther and like write the note about who killed you, but like you're gonna go down at the end of the day, versus this one is like a little bit more forgiving in that you can actually recover from it right now. So there's definitely further depth of further depth we can get into there.
Gotcha.
But I think this will, and we could, if we wanted to, we could do kind of a further thing here, but this will, I think, take care of us for now.
Gotcha.
So we've got this uninterruptible, and then I don't think we actually implemented it, but if we wanted to, let's see, interrupted, so we didn't implement it. So we could just implement the converse of this. So we could also implement interruptible. And this is basically going to be the same thing, except we'll kind of work on our logical negation here. Or maybe we actually have, do we have fancy? No, we don't. Okay, we have the other operator. So we'll stick with negation. So if we're not interruptible, which means we're uninterruptible, then we do something. Otherwise,
do we just want to flip all the uns to non-uns?
Exactly. Exactly. Set uninterruptible. Okay. All right. So now we have this ability to regionally control interruption. And that becomes pretty important, because this is kind of going to be the basis for implementing these operators for resource safety. So in ZIO 2, we have this, it's kind of like the fundamental operator for resource safety is this one called acquire release with. And so what this one's going to do is it's going to take three, I'm showing my, we don't have any R yet. But so it's going to take this acquire action that can fail with some error, and it's going to return this A. And this A is basically going to be the resource. So it could be like a file handle, or it could be something else that we want to do something with, but then we want to make sure we close it when we're done. And then we're going to have this release action that is going to have access to that resource, and is going to do something with it that can't fail, but it don't care about what value it returns, because we're just going to do it for its side effect. So this is going to be like open the file, close the file. And then it's going to have this use action that's going to have access to the file, and is going to let us do something with it, like read its contents. And then eventually we'll get back the contents. And this is kind of the big thing that we want to be able to implement here. And the semantics that this is supposed to have is that acquire is uninterruptible, release is uninterruptible, and use is interruptible. Right, so when we're opening the file, we don't let ourselves get interrupted while we're opening the file, because then we could get into some inconsistent state where like we've done some of the work of opening it, but then we never like do the closing of it. So this is uninterruptible, and this is uninterruptible because we potentially want to do this even if we're interrupted. The whole point of this is to say, even if we're interrupted, no matter what, we release the resource. But then we want to make the use, the like reading from the file, we want to make that interruptible, because otherwise what's the point of interruption if we can't interrupt ourselves most of the time when we're using something and we decide we don't actually need that thing. So we could start to work towards how we want to implement this. And so let's just, we can start almost like playing with it a little bit. But like maybe the simplest thing we could do is like not even worry about the interruptibility yet, just kind of what do we need to do with the types here to make this work. And so what we could do here is we could say, okay, well, I need to run the acquire, at least my simplest world. And that's going to give me this A. And then I want to use the A. And then I could use the ensuring thing, or maybe right now I'm just going to make it kind of a little bit more explicit, just so we kind of see it here. But so I'm going to do we'll cause ZIO here, and so I'm going to have either a cause or a B. And so if I've got a cause here, let me actually make this, let's see, we do have exit. So let me actually make this slightly more general. So the most general version of this also gives us access to this exit.
I see.
I feel like this thing is not auto-compiling as fast as it should be, but I wonder if I'm on the right project here. Projects, project, yeah, scratch. Excellent. Okay, now it's like more real. Okay, so if using failed, then I've got this cause. So then I want to run my release. And I can give it the resource. And I can tell it this thing failed with a cause. And then I can either do flat map or the star arrow. And I can fail with that. And then if we succeeded with the value, I can do this. And then I can actually, there's a little bit more even we could do if we, so what we do in the real ZIO is there's a possibility that like the use fails and the release also fails. And so we can combine those two failures together, but that requires to have the cause.both and the cause.mn, and we haven't implemented that. So we'll just kind of note that for now here. Okay, so this is like the basic like desired semantics here, but this doesn't handle this interruptibility and uninterruptibility yet. But we can start to do that with the operators we have. And so we could kind of note here that, I mean, one way of like simplifying this description is I want everything to be interruptible except for this one here. So let's try doing that. So we could say, okay, well, that's easy. I'll just throw a ZIO uninterruptible around this whole guy here.
Mm-hmm.
And then we just said, this is the part I want to be interruptible. So I will just throw a uninterruptible, or excuse me, yeah, an interruptible around here. And I'm pretty good to go here. Now, can anyone suggest something that might be wrong with this?
Ooh, that's interesting. Well, I don't know the answer, so let me just talk it out loud and see if other people are gonna go through the same thought process. So we're making it uninterruptible at the beginning. So this whole thing, and then if this blows up in some way, we'll set it back to whatever the previous interruptibility status was. So we're going to acquire uninterruptibly, then we're going to flat map uninterruptibly. So that's maybe, it's always a little tricky with the, I think sometimes, especially if you use a for comprehension, the idea that a flat map is its own sort of effect that can be interrupted separately is sometimes a subtlety. I'm not sure if that's the culprit here. Maybe not. So then we're getting the A. Then we're becoming interruptible here. And that seems right. Going back to being uninterruptible, folding that. Yeah, I don't know. Obviously, our release is uninterruptible, but we want that to be the case. Yeah, does it have to do with that flat map? That's the only sort of thing that I'm not sure if I completely see. But yeah, I don't know the answer. Maybe somebody on Discord is clever, but no one wrote anything.
Oh, okay, all right. So it actually has to do with this dot interruptible here. And the way you can think about it is what happens if I do something like ZIO dot uninterruptible. And then within this, I guess maybe I'll actually make it real code, so it won't work. But I'll do. So if I have something like ZIO dot uninterruptible, and then in here I do ZIO dot acquire release exit with. What is weird about this potentially?
So is it, so I guess we can be interrupted in here, obviously, and that's going to cause this to fail. I see. And while we're catching the interruption, then we're throwing the interruption again. So it's kind of acts as though we got interrupted in this uninterruptible region. Is that it?
Yeah, that basically what we're doing here is we're kind of poking a hole in this uninterruptible region. This said, I want everything to be uninterruptible. And let's imagine this was kind of the user code, and this thing was embedded into some kind of library code that is like, ZIO open file or whatever. And so, yeah, by doing this, we've exposed interruptibility within this region that is supposed to be uninterruptible. And another way of maybe thinking about it is this interruptible was like too strong of what we really wanted to do here. And admittedly, maybe part of this is my fault because I was maybe being a little bit colloquial here in my description, is we want to run these two things uninterruptedly. And we just want to leave this one alone, right? If we were already in an uninterruptible region, we don't want to mess with it. Most of the time, we're already going to be in an interruptible region. That's kind of the default. So that's why, like, colloquially, this is like an accurate thing to say. But if I'm in a block like this, I don't actually want the use to be interruptible because this person out here said they want it to be uninterruptible.
Yes. So we wanted to restore the uninterruptibility status. We want some kind of mask, if you will.
Exactly. So you can imagine up here, like before this, you could say I could do like get interrupt status, right? And I would have some kind of interrupt status. And what I would really like to do here is not necessarily set it to be interruptible, but set it to be whatever interrupt status it had out here. Most of the time it's probably interruptible, but I don't know for sure what that is. And so that's where this uninterruptible mask operator comes in. And so what that's going to look like is, instead of just giving us this function, the ZIO here that's going to be run interruptibly, it's going to give us this thing that we'll call a interruptibility restorer. Say that 10 times twice, and we don't even know what that is yet, but maybe I'll just make it a little steel trait right now. And that's going to give us, so we're going to get access to that when we run this effect, and then it's going to give us this back. And so this interruptibility restorer is going to have one method, and we could either call it, I mean, we could call it like restore interruptibility, but it's kind of works a little bit more nicely if we call it apply, because then we just get to use our nice syntax here. And right now I'm just gonna leave this TBD. And so what this is going to do then is down here, instead of using this interruptible, I'm going to change this to uninterruptible mask. And that's going to give me this store thing. And then instead of ZIO.interruptible, I can just do restore. Oops.
Something, yeah. Some kind of sync error. Anywho, it's restored.
So now if I can implement this uninterruptible mask thing, then I've basically got this acquire release thing down. And I think once we do this, we can maybe actually go to the actual ZIO, and I can show you like how much this looks like the exact implementation of acquire release in ZIO itself. So let's think about what we need this, how we want this interruptibility restore to work here. And maybe I actually won't implement this here. So let's try implementing this. So I think just like the previous one, we might want to start with this with runtime flags. So we want to get this interrupt status. And then maybe we want to have something here that makes one of these. And
from flags?
Maybe, yeah, I mean, and maybe I'll call this thing original interrupt status.
I don't know if we made an interrupt status, did we?
Oh, did we? Maybe we just had a Boolean, so that's fine.
I think we just, yeah, a Boolean, yeah. Just say is interruptible.
Yeah, or maybe let's call it like original interruptibility, just so we're like clear on. And so this is going to give us an interruptibility restorer. And so this could be a new interruptibility restorer, and we just have to implement this one method. And so here we could just say if, well, maybe we should call this originally interruptible.
Yeah, exactly. Originally interruptible.
So if it's originally interruptible, then we're just going, then what it means to restore it is to make it interruptible again. And otherwise, what it means is to make it uninterrupted. So now that we've got that, so we could say maybe, oops. Oh, you got it.
All right. So yeah, I'll do that. Yeah, so interrupt. Oh, well, here we go. Yeah.
So now that we've got this restorer, we can probably take most of our other logic and we can just basically apply the same thing. So if we've got that, we could do the same thing of if we want this to be the uninterrupted one. So where's our uninterruptible we had?
In this case, wouldn't we just pass it to wouldn't we just call the F at this point inside of uninterruptible mask with our restorer?
Well, so that's going to give the inner function the ability to restore it.
Oh,
but
we have
then
to.
we still need to make the whole thing uninterruptible other than the restore.
Yes, yes,
But
yes.
if we want to, we could actually delegate that to the uninterruptible thing we already have. So we
Sure.
could just do uninterruptible F restore here.
Cool. Cool.
And so now when we do this here, if this is in an uninterruptible region, this whole thing is going to be uninterruptible, including the use. And you can think of like these, the acquire and the release are forced to be uninterruptible by acquire release itself. The use acquire release says, I don't have an opinion on whether the use should be uninterruptible or not, but someone already said it should be uninterruptible, so I'm going to respect their decision. It's a more humble operator.
That makes sense.
All right, so why don't, we've done a decent amount of coding without actually doing an example. So let's make sure this works for us here. So why don't we define some simple resource, my resource. And so this is going to be ZIO acquire release exit with. And I often like using kind of braces for these. We'll at least do the first part of this. This one is premature at this point. But then the second one is the release action. So we got access to this thing. And right now, maybe I'll just ignore it. Yeah, maybe that's fine. We'll say we released it with this exit value. And then the final one is where we get to do something with this. And right now, maybe I'll do dot succeed, print line using, and then ZIO.never. So this is going to very quickly, basically immediately acquire this resource, and then it's going to get stuck using this resource. So we can imagine this is like it's some like really big file. We're just reading. And meanwhile, we're going to start this off, and then we're going to decide, well, we don't actually care about reading from this anymore. And what we want is this release to get printed anyway.
Mm-hmm.
So let's do val my resource example, and we can do a for comprehension, and we could say fiber and my resource.fork. And then let's just like wait a second just to let it go, and then we'll interrupt it, and
Wait another second.
Then print like all done.
Cool.
And so if all of our little adventures here have worked, we should see that this is getting released. And otherwise, we'll have a fun little debugging session depending on how much time we have to.
Not today.
All right, so let's see. And then the way I've got this set up, I think right now with these, we've got to do my resource example, .unsafe run sync. And then we probably need to make sure we're not doing something else that we're running. So this is actually ready to go. All right, so let's try this.
Oh, up there. No more exit.
Oh, yep. Okay. And there we go.
Acquired.
Other than, I guess, our inconsistent capitalization, that was pretty good. And so that's exactly what we want from these types of operators. And maybe, let's see, I wonder if my VS Code here is going to support me in clicking into actual ZIO source code. This is like to some recent discussions about tooling. This will be a highly uncertain thing. Yeah, so it seems like that may be a no-go. Give me 1 second. Let me just open another window here and do another screen share. And I want to show you the real implementation of acquire release, and you'll just see how it's pretty similar.
Cool.
Let's see. And I think you may have to switch over to the the Zoom here.
Yeah, look,
But
I'm
can folks see this?
Timeout 2. Yep. Acquire.
Yeah, so let's go to acquire, release, exit with. And so one thing is in our simple version, like the type inference is not always perfect because we have the same type parameters appearing in multiple places. So the type inference is slightly better if you do this partial type application thing, which I think we actually had a previous symposium we did on that. So it doesn't have that much implication as a user, other than if you want to do this, you have to click through a couple of these to find the actual implementation here. But here's the actual implementation. And let's walk through it. So we're using that uninterruptible mask operator, which is the same one that we implemented. I mean, this is the official version, but conceptually the same thing. And then we are acquiring it. The only reason these parentheses are here is because this thing just suspends each of these things in a thunk. So a little bit of the same trick that we did in our earlier session when we were implementing like succeed. But so we're running the acquire, we're flat mapping it, right? Just like we did in our real example. Then again, they're just doing the suspend succeed around it to be extra lazy around this in case the construction of the ZIO itself throws an exception. They want to suspend that, but that's not doing anything other than that. So they're restoring the interruptibility and they're using this thing. And then they're just using a slightly different set of operators. Remember, we use the fold cause ZIO to get at the failure or the success. They just did the dot exit operator, which basically just takes the whole failure and success and stuffs it into the success channel and then flat maps it. But that doesn't really matter here because as long as we're outside of these restore parentheses, we're uninterruptible. So it's just another way of doing the same thing. And then we've got that error and we run the release. And then this is the one place where things are slightly different just because we have this ability to combine the errors. And so we run the release and then we look at whether the release succeeded or failed. And if the release failed too, so we have two failures potentially, then we combine those together. And if the release succeeded, then we just return the original exit value. So it's like very slightly different, just in that like it's using the exit versus we kind of had the two cases down here for the success and the failure, but that's like a completely just like stylistic difference. Like there's no significance to that.
And quickly, again, you mentioned about the suspend succeed, but that's too, like, what would the consequences be of not having that as since we are in the flat map, would that sort of defect? What's the difference in semantics if you don't have that?
So here, like if you didn't catch the suspend succeed here, then you'd actually throw an exception here, and then you would just kind of be done, and then you could leak the resource because
of course.
You've already acquired it, but you're not going to run the rest of this stuff.
Sure, you would die up there, but you wouldn't. Yeah. Okay, gotcha. Makes sense.
Yeah. So someone did a fun PR when they added that. I think they called it like beast mode error handling or something. I think that was a Regis special.
Yeah, it can be a little tricky
right.
thinking through these very advanced subtly. Like you really have to understand all the semantics, and then. But yeah, this is basically it. Okay, it probably gets more complicated, but if you can understand this, you're pretty good to go with reading implementations of ZIO source code.
Yeah. All right. Let me close this, and I'll go back to the previous screen share.
Cool. Mm-hmm.
Oh, did I? Yep, the right one. I just need to navigate there. Okay, so let me go back here. So that's what resource usage looks like with our toy ZIO here. So I think at this point and I think the other nice thing you can see about this is like we're starting to get to like we've got the building blocks and we're able to be at a little bit of a higher level where like today we actually didn't have to implement anything in the runtime itself, and our code was a lot easier to work with, which maybe can be evidenced by the fact that we did not have to do any manual debugging after we did our coding. And that's kind of the nice thing, that you get some of this lower level stuff in place and then you do the hard stuff once.
For sure.
So I think we can go back here and we can kind of do the little check mark thing on these two. We actually got through that pretty quickly, so maybe this is a good time to check in with folks on, I mean, I think we've obviously covered a lot of stuff over this series on different things. Is there anything that people want to spend a little bit more time on that we glossed over a little bit? Or if people have any kind of questions about, like, not that we can necessarily implement everything, but like, how would you approach implementing something based on this, or just any ZIO or other questions in general? This is a great time.
Yeah, maybe I could just make notes for potential future extensions. I don't think we'll have enough time to do the environment today, but obviously that's something that we've left.
Yep.
But we've kind of touched that before. I don't know if that's so different. And then something I find interesting is fiber refs, sort of the implementation of those. I've looked into it, but I'm not sure if it's entirely obvious. I mean, we've done a Zymposium on fiber ref, but we have this data type called a ref, which acts like, the ZIO version of a variable, essentially. It's concurrent safe variable. And then a fiber ref, it's just a ref, but on fibers. But if you think about it, the fiber ref can't actually hold the values because it might be many values. So what is exactly the fiber ref? And could you maybe give an intuition for people who might be confused about that? I'll mean to see if other people have questions, but while people type any, I think that could be interesting.
Yeah, that'd be a really cool one. Yeah, so the fiber ref, like, you can almost think of the fiber itself as being like a key that just you're going to look up a value corresponding to it. And whenever you want a value, what you do is, like, every fiber has its own like map that has like the value that it has for each of these fiber refs. And you just basically ask the fiber, like, look in your map for this key, what's your value for it?
Yeah, it's kind of a clever thing.
Yeah, I mean, I'll say we probably, depending on if people have questions how much time we found it, we probably could implement that, at least a simple version of it.
We got 20 minutes. Let's go, Adam. Go.
Does anyone else have anything that they're
I don't see anything
interested in?
So silences, I assume they're all hankering for fiber refs. I'll check the Zoom chat as well, but yeah, nothing.
Okay.
Nothing
All right. So let's maybe try this. So we got fiber. Let me just kind of get down to the end before we have our little examples. Oops, not too far, I think. Yeah, too far. Okay, we have cause, runtime flag. Okay. So let me create some type for a fiber ref. And the fiber ref is going to have this type fiber ref of A. And so the A is going to be the value inside it.
Mm-hmm.
And so when you make one of these, you're always going to give it some kind of initial value, which is the value that it's going to have if no one else sets another value for it. And this is typically going to give us a ZIO that can't fail, and it's going to return one of these fiber refs of A. And then this fiber ref going to have a bunch of methods, but I think we'll just start with maybe the simplest of it's going to have a get method that's going to return a ZIO and A inside it. And it's going to have a set method that's going to let us give it an A. And it's just going to turn this. And so what we're going to do here is this is one where we're actually going to implement another primitive in this ZIO fiber to support this. And we're going to need a little bit more data for this. So basically, like an intuition you have for these fiber refs is they're a little bit like thread locals. So every fiber is going to have their own copy of these fiber refs. And so just like these other things, we're just going to need a new place to kind of store these values. So we're going to have something like, maybe we'll call it private var fiber refs. And this is going to be a map from fiber ref of some unknown type to any. And the reason it's typed this way is each of these fiber refs are going to have their own type, right? One might be a fiber ref of string that's like the name of the fiber. Another might be like a number that's like the parallelism to use. So every fiber ref is going to have its own different type here. And so when we put them together into the map, there's no way to combine those types. And the best we can do is just forget them, which is what we do with this underscore here.
And it's going to be correct by construction, sort of like when we did as a while ago.
Exactly. We're going to have to maintain the invariant that for every entry in this map, the actual type that goes in here is going to correspond to whatever this type is supposed to be. So this is going to actually store these fiber refs. And then we're going to need some operator in the ZIO runtime to work with these fiber refs. And there are a couple of different ways we can encode it. But I think one way we could do it, let's see, it's in ZIO.
It's kind of be like update runtime flags, just give it the map, let it do what it wants.
Yeah, exactly. I think the only thing we either, if we just do update, then we don't have, depending on what we do, we may want to have a way to get. So we might want to have it be like modify runtime flags. But yeah, I mean, or we could have a separate get and set. That's where I say they're like slightly different encodings. Gotcha. But
I like modify. Yeah. And I guess, yeah, we could have kind of done, no, I guess it would have been weird to combine those, but yeah.
Oh, but not modify runtime flags. So we modify fiber refs.
Yes.
And so, yeah, I mean, we could also do it the same way here, but I think maybe this is fine. So this will return an A. This will take an A. Yeah, exactly. Just kind of follow our extension, and this will return an A.
Cool.
So then if I've got that, then I should be able to implement, go to my fiber ref. And maybe here I'll actually implement modify. And so this will take B and it'll give me back B and the A. And so here, this could be ZIO dot modify fiber refs. And so we're going to we have one more concept here, which was kind of implicit here, but we're going to have this concept of a default. That's just going to be an A here. And so this thing is going to give me access to the fiber refs. And then eventually I need to return some result and some new fiber refs. And so here's where the idea of this fiber ref as being a key comes in. Because what we could do here is we could say, so maybe something like val current value is equal to fiber refs dot get cells, and we'll do a little self-reference thing. And why is this? Did I just hold on? Class modify. Oh, see, I was very silly here. So this right now is this map from this fiber ref underscore to any. It would probably be cleaner if we wrap this up in a type called fiber refs that actually exists in ZIO, but I think right now we'll kind of roll with that.
Oh, and it equal. There we go. Okay.
So here we can do get, or really, let's see, I think we can do get or else, exactly. And so if it's not in the map, then we'll just return the default value. And then we're going to have to kind of rely on the fact here that this is actually an A value. So we'll cast that. And if we wanted to, we could kind of wrap this up in something that did more of this in the runtime. So we didn't do it here, but either way, it's fine. So now we've got this A value. And then we could say val B new value is f of the current value. And then we could return that summary value. Maybe I'll just call that summary to be extra clear here. And then, yeah, we're just going to update the fiber refs with the new value. And then cool. I think Kit's already gone ahead and implemented set and update and get in terms of modify here. So now we're at the point where we've got to actually implement this modify fiber refs. So let's go to the runtime here, where we have all of our little pattern matching. Case ZIO dot modify fiber refs. And so what we could say here is that val A, and maybe I'll call this updated fiber refs equals f fiber refs. And then I could set the fiber refs to the updated, I guess I should call this fiber refs. And then we can just do current ZIO equals ZIO.succeed A, because that's the type that we're supposed to be returning here.
Perfect. Nice. So pretty easy. I'm guessing there's the we have to deal with forking as well, right? For propagating these, because every time...
yeah, I think that we will say is outside the scope of our little 20 minutes here, but we can have another very interesting session on this.
Okay.
And so one of the interesting things here is the make here, actually, we're going to wrap it up in a ZIO effect just because this is kind of allocating something and we want to be like safe that way. But we really don't have to do a whole lot here. We can just make a new fiber ref that has this just initial value, because all this is really is being a key, and we're basically just using the object identity of the fiber ref as the key here. So let's see, again, with kind of some caveat of we're doing a bunch of stuff without having tested it yet. Let's try to actually do this. So let's say val my fiber ref example. And so let's say, I'm going to say for fiber ref and fiber ref.make 0. So this will have an initial value of 0. And then, yeah, let's do something really simple. Let's set it to 1. Maybe, okay, let's update it. Modify. Okay, perfect. That'll give us a summary value.
Perfect.
Okay, and then I need my little
and maybe example. Something.
Yeah, I know this is like super simple because we haven't even done anything with like forking yet.
Yeah, I'll make another one on the above so we can go for the next example, but definitely go with this use fiber ref.
Yeah, and I think that one I don't think we really have the infrastructure yet for the forking to work. Okay. I'll wait for you to do your typing just so this
Okay, yeah. Let's see. I'm just going to
actually
do
compiles and can run.
copy that logic out, and then we can like call it twice and fork two things. So at least we see that like the refs aren't like normal refs. Is it sad? What have I done? Fiber ref.
Oh, and show we can do two of them. Yeah.
Just that. That's just that, not the whole like forking and inheritance. I've screwed something. Have I screwed up, or it's just late? Okay, it's just lazy. But anyway, let's run this one first, unless I have too many squigglies.
Okay, we're good.
Gotcha.
All right, so let's try running just the really simple one first. Let's make sure we. All right, so we've got 2. So let's see. So 0, we set to 1, we updated to 2, we modified, and we just returned the original value. So that's the expected value. Great. And now let's use Kit's thing. So we created this fiber ref, and let's use it twice on 2 different fibers.
Okay, we do a zip with parse, so let's do that maybe. Or I could do .fork and then just do that a few times. Yeah. F1, F2, F3. Yeah, I guess that. And then maybe I'll just join F3. Or I guess I could not fork it as well. Let's do that.
Okay. So we've got 3 of these. And okay, we updated the examples.
Yeah, two. So they each get a fresh copy, which is obvious. But I think if you like
Yeah, I mean it's obvious when you think about it this way of like the fiber ref is not actually a ref that has a value inside it. It's just this like key that like we're going to use to look something up. And if it's just a key and it doesn't really have any value except for that default that we use if there's not anything, then you give the same key to multiple people and they may give you back different values, right? It's just like you're looking up something in a database and Adam may have different values or balances if you look up his accounts in different banks. But yeah, I think when you say like ref, you kind of think, oh, it's like one thing.
Well, yeah, it's a neat I don't know, because the semantics of a ref, it has all the methods of a ref. You kind of can use it in the same way, but yeah, when thinking about the details of how it works, it's like, oh yeah, it's a map. So you probably wouldn't want to call it like fiber map key, because that would be very confusing to use. Like it is nice to piggyback off of the semantics people are used to. It's cool. Great, and we did it in 16 minutes.
Right, which is also a cool thing of as you like have like once you have some of the infrastructure for this, you can knock out cool features like this pretty quickly.
Yeah, we just keep adding things to our this is great. It's really paying for itself. It amortizes nicely. Well, we've done a session on FiberRef fairly recently, and so I guess one might imagine, I don't know the intricate details. Maybe there are a lot of complications, but obviously we needed these 2 extra methods besides default for how to deal with forking, how to deal with joining. Clearly, there's some like logic. Is it way more complicated than just adding some detail around sort of the async fork call and then back when you join? Is there a lot of
no? I mean, really, the only thing we haven't taken into account of here, which does have some subtleties to it, is right now. So, like, let's say I do fiberref dot. Yeah, let me say I set 1 here.
Sure.
And so let's try running this and let's see what happens. And do each of those fork, or why did that last one? Oh, because you're setting it. Sorry, yeah.
If we updated like this,
that'll. Yeah. Let's run this. Perfect. Okay, so you see we got 2, 3, 2 here, and the 3 we kind of makes sense to us of like we set it to 1, and then we add 1, 2, add another 3, we print it out. So the 3 makes sense. Mm-hmm. The 2 values that are 2 here make a little more sense with our internal logic, but maybe don't really make sense as much. Because right now what we're saying is every time we create a new fiber ref, it starts out with that map being empty. And we can see that if we went to class fiber runtime and we look at this fiber refs here, and we see it just started out with the map being empty. Now, a really easy improvement we can do to this is, let's see, where do we have our fork method?
I think it's an async, right?
So right now, when we make a fiber runtime, the only thing we need is just the effect we want to run. But as we get more sophisticated, we're actually going to want to put more stuff in here. And so here, maybe I call this like fiber ref 0. And this is going to be a map from fiber ref underscore to any. And then when I start off, instead of starting off with an empty map, I'm going to start off with this fiber ref 0. And then I'm going to the compiler to help me. And I'm going to get this error message here when I start this thing. And so I am going to see if I just unsafely run something, then I'm going to start with an empty map. But when I fork a fiber here, let's see, we may not have quite the right way. Oh, so then what this is going to need to do is this is actually going to need to be updated to get the fiber refs.
Sure.
So I could see if I can just do this on the fly here. So this is kind of going to need to be ZIO dot modify fiber refs.
Luckily we have that, so that's great.
Yeah, and it would be nice if we had a more like specific one if I didn't have to directly call the constructor, but you know, we're kind of going to do what we're going to do here. And so then I can give this the fiber refs.
And then just tuple this up with fiber refs, is that correct? Because I believe it's going
Yeah, and I think then we're going to need one more flatten on this whole thing, because this is a ZIO. So hold on.
I'm not sure if we have flatten either.
Oh, you can do flat map identity.
Yeah.
Let's see if we can.
Is effect unhappy? Maybe it's just delayed. There we go. Cool.
Okay. So let's try running this again. Let's see if that will. Yay. Okay, so now all of these are 3. So that's a little bit more of the expected semantics, or this is like half of the expected semantics of we generally expect that when we make a change in this parent fiber and then we fork it, this child fiber is going to start life with the value that it got from its parent fiber. So that makes sense. The other part that I think we probably won't implement today is that when we join a fiber, we want to get its changes. So if this fiber updated the value, when we join it, we normally want to pull that updated value in. But then we actually, as we work with it more, we want to have more ability to both customize that. Maybe we don't want to just replace one with the other. Maybe we want to combine them somehow. And when we really get to thinking about it deeply, we get to this point where we don't just arbitrarily want to apply changes, but we actually want to think about these as patches. And there's this whole like patch theory and patch algebra that we can apply to like how we define these patches and how the patches combine with each other and the laws that's supposed to follow. And most of that you don't really need when you just define your fiber ref, but under the hood, it has some really positive effects of, it can prevent concurrency issues. If you can imagine if you have 2 different fibers that made 2 different sets of modifications, and then you join them both, how do you like join both those modifications in a way that makes sense? And how do you have the flexibility to do different things that you want to do with these? Because sometimes you may want to apply some type of custom logic, and if you just hard code it to like, well, you keep the parent value, you keep the child value, it's not powerful enough for all the use cases you have. So yeah, that's probably another Zymposium if we want to do it sometime. But that's what's missing from this simple fiber ref implementation.
No, that would definitely be a fun deep dive. But this is a great pedagogical model, reference implementation at least for because I think a lot of people probably don't think about how fiber refs are implemented. So that's good. 21 minutes, easy.
Yeah.
Well, cool. So I guess that's probably, I think we're going to put the ZIO from scratch on pause for a little while because we got through that. I mean, it's all one topic. I think we've done 6 or 7 consecutive sessions. It's very interesting, I think, but variety is nice. Variance. Yeah. We embrace variance here. So let's do something else next week. Yes, to preview it. I'm still working and studying on this, but to force myself to complete my extracurricular activities, I would like to do sort of something a little not too different. I mean, here we're implementing an effect system, but it's still kind of high level, right? We're sort of deferring to all the Scala machinery of threads. We're transpiling to some degree. We're compiling our code, but into another very high level. So I've been reading more about, trying to get lower and lower levels, reading about, machine code and x86 and whatever, ARM and all that stuff, and LLVM. And it would be fun to do something closer to the metal. It's really just the same damn process over and over again. We're just, you're just compiling again from a higher level language to a lower level language. It just becomes more and more painful as you go. And you have fewer and fewer abstractions to work with as you go from the high level to the low level. But it's kind of nice and reassuring that it's all just the same a thing over and over again. So yeah, something along those lines. I don't know if we're going to write an assembler or a CPU emulator or something that uses LLVM, make a silly little language, but we should at least have fun and hopefully learn something. I'll certainly learn something. And now the pressure's on for me to come up with some testing for next Friday. So that's the general domain.
Awesome.
It'll be a good time.
All right, well, I'm excited. Have a great night and weekend, everyone.
Take care. Bye, Adam. See everybody.
Bye.